Dear ladies and gentlemen, welcome to the training workshop on biogas from organic waste. This is the part development of biogas projects and economy, and my name is Jan Liebethauer. As always, you will find my contact data on the last slide, and in case you have questions, don't hesitate to ask. First of all, I would like to introduce you to the content of this presentation. I'll start with an introduction, then I would like to highlight the need of a feasibility study for biogas project, discuss a little bit substrate characteristics, mass balances, gas utilization and digestate handling. And last but not least, there will be some slides on the economy of biogas projects. First of all, when you go for a large investment, for a large project, and this holds true not only for biogas projects, you need to make sure, or you need to pay attention to the impact you have on the development on this project during the development phase. And that's why I have put in here this little figure you can see on the right hand side here, just to visualize that during the project your impact on the costs and also on the type of technology, of course, is constantly decreasing. So once you have made your major decisions on the technology and on the construction company, things like that, the less impact the less chances you will have during the project to change this. And then at a certain point, you will reach the so-called point of no return. So you just have to follow the route based on the decisions have been made previously. And according to this, of course, the expenditures will develop. That's why when you come to the decision that you would like to look into a biogas plant, make sure that you follow this idea with a feasibility study, because here you really can check on different options. You really can make decisions on the technology, on the components you decide for, and how the overall plant is organized. And these are decisions which have a great impact on the costs and also on the operation of the biogas plant. So I would like to really emphasize here on the fact that the planning phase of such a complex plant has to be done with a lot of care, and you really have to take your time to make your decisions here, because otherwise you might regret in later phases that you have been doing at a certain point not very good decisions, and you will pay for that, that's for sure. Second important point is biogas plants rely on the substrates. So the characterization of the substrates, the availability of the substrates, and, very important point, the gas potential of the substrates are very important points to check very early on. Then, of course, construction site is a very important point to choose. Also the infrastructure, logistics of substrates and digestate. Then, once you have made this early on evaluations and checked upon these points, then you need to select an appropriate anaerobic digestion technology. You've learned in the previous sections of this workshop a lot about technologies, advantages and disadvantages. And here now you have to select according to the substrates mainly what technology you would like to apply. And this includes, of course, also the type of gas utilization, CHP, upgrading, fuel provision, all these points you have to decide on. Then you come to this point where I would recommend to go a step back and think, okay, what type of decisions we have made here? Do we know enough to really go now into the detailed planning? Are the decisions we have made well-founded, that we can make our investments or can proceed with our investment decisions here? Public participation, this is a very important point, depends of course on the country and the location of the plant, but in Europe this is more and more gaining importance, and you should make clear that people living in the surroundings of the plant fully understand what's coming up here and that they accept this. And this is an important point which has to be considered early on in the project phase. And then we come to the actually engineering, the planning in regards of the permission for the plant, the necessary detailed engineering for construction of the plant, execution plan, timing of the different steps, things like that. Then we come to the construction planning and the construction of the plant. You need permission for this construction. And once the plant is constructed, you go to commissioning of the plant, proof of performance. Very important point. When you sign your contract for the plant, make sure you have made a clear agreement on the proof of performance, what the contractor has to prove, how the proof of performance is conducted, and then last but not least is the acceptance and takeover by the plant operator. In parallel to all the steps, you have of course to kind of see that you get in contracts for the substrates and also for the digestate. So you want to make sure that once a plant is constructed, you can start up operation and you have your substrates under contract, and on the other side you know how you get rid of your digestate or how your digestate is being used in agriculture or other application areas. Now I would like to discuss a little bit more in detail again on this point what I said previously, the major points of influence on the biogas plant. And here I would like to highlight or mention some major points where planning and construction of biogas plants has been inappropriate in the past, or where construction malfunctions or construction mistakes have been done. First of all, I would like to state here that very often the technology doesn't fit the substrate. You've learned a lot of technology options, a lot of components which you can choose of for a biogas plant, and it's very easy to select a pump or a digestion system which fits for liquid substrates, but not for solids, for instance, which fits for substrates which contain no inerts as stones, or which doesn't fit to stones and inerts, things like that. So once you have built in a not fitting component, then you will face a lot of wear and tear. You will face a lot of standstill of the biogas facility because stones will block your pump, stones will make your maceration system dull, things like that. And that's why make sure that your substrate really fits the technology. Components do not connect to each other. This is simply wrong dimensions. You have planned with a substrate which you haven't gotten under contract, and you have to buy other substrates which are not fitting to the dimensions you have built, or you simply have misdimensioned some components, or a component requires a certain pretreatment or a certain step ahead which you haven't in the plant, and then this causes trouble. Again, the example of sand or stones in the process. You might have a macerator which requires clean substrate, and so if you don't have a removal system for your sand and your stones, then this will cause problems. So a biogas plant is not or cannot be built simply by putting together some components. I think a biogas plant is all components working together and matching each other. This is very important. Very often components from other applications are applied in biogas plants. An example are pumps, for instance. They might work for water, but they do not work for substrates in the biogas process, or mixing systems, which might work for very liquid digester mediums, but they are not working in a very viscous situation with high total solid content. So make sure that the components you're buying have been tested in biogas applications. Lack of monitoring and control is often an issue if you have specific substrates, and process control requires action, and you don't have the monitoring to actually control or to observe what's going on in the plant, and this causes a lot of issues in your biogas operation. Example here is H2S concentration in the biogas. You don't have an H2S measurement in your gas analyzing system, and all of a sudden your CHP breaks down due to corrosion. And this is an example of lack of monitoring control. With a simple sensor for H2S in the gas analyzer, you would be able to recognize, identify the problem, and go on with some measures against this problem. Lack of necessary maintenance and replacement. This is also a topic that some plant operators simply run the plant until it breaks down and then they repair. But the consequence is that you will have very often breakdowns and a lot of maintenance and repair, and every downtime means that you're not earning revenues from your energy production, and that's why such maintenance and replacement breakdowns cost you double. They cost you once because you have to replace broken equipment, and they cost you because you have no revenue during this time. When you go for a feasibility study, then first of all you need to check on what substrates you would like to use or what substrates are available for your biogas plant. In the long term, it is of course not only the question what substrate you have in your first year or in your second year. The question is what substrates do you have in the next 10 or 15 years? Because most equipment you apply in a biogas plant has a very long time of operation, and then you make sure that even if your substrate will change during the operation, your system is able to handle these substrates. So you shouldn't look only for the first 1 or 2 years of operation. Consider what your long-term idea of substrates in the biogas plant will look like. Second, the quality of the substrates. Here I'm talking of gas potential, but not only gas potential, also characteristics like the content of total solids or the content of disturbing material, as I already mentioned, sand and stones, metals, plastics, things like that. Make sure that you really have a good estimation or even a good analysis of your substrate's characteristics in order to be able to select appropriate technology. Costs related to substrate. You might need to purchase substrates. You might need to haul in substrates, which is related to costs. You might get a gate fee for substrates if it's waste material. This is an additional income. Depends on the substrate. However, whatever costs come directly with the substrate, additional costs are pretreatment costs. Pretreatment costs as, for instance, cutting and milling or separation of disturbing materials. Also have to look at these. What is necessary to actually to condition the substrate for the process, to make them fitting to the process. These are also costs which you should consider during pre-evaluation of your process. And based on these evaluations, you can go for technology screening, which technologies are matching actually the conditions which result from your substrate characteristics. Second point is infrastructure. It starts with transportation and logistics. So if you have a lot of haul-in substrates, make sure that roads are properly and you will not get a lot of trouble with people living nearby. Grid access, either electricity grid or natural gas grid for feeding in the biomethane. How stable is the grid? Potential heat sinks, if you have a CHP unit at your plant, where can you use the heat? Or what heat supply you need in case you have a biomethane production. A point which is, I think, in Egypt very important is availability of technology supplier. You might select a very good technology, but if you have no technology supplier in your country, it will take a very long time to get extra parts, to get supply. So you might choose a technology which might be not as superior or which characteristics are not as good, but you might get faster support, and the infrastructure for this technology might be better in your country, and then I would rather recommend to go for such a technology. And last but not least, where you would like to apply your digestate, what to do with your digestate. Very important point, if you build a biological treatment plant, make sure that you have a plan for the application of the digestate. Next point I would like to discuss is legislation. This is in general permissions and restrictions for technology, substrates and digestates. So when you look at technology, then there might be certain conditions for operation of, for instance, gas holding technology, as we have here. So gas which is potentially explosive, so there are common restrictions with that. There are also restrictions for the substrates, if you think of waste material, but also agricultural residues as manures require certain technology, certain treatment technology options. And last but not least, the digestate is also usually in the countries coming with restrictions, conditions which you have to fulfill. You have to analyze all these legislative conditions and then make sure that your plan, investment follows these conditions, and if not, you need to start with the authorities a discussion in order to get the appropriate permissions. Economy, important point of any feasibility study. Of course, you will not go into a very detailed study here. However, you might evaluate investment costs for your equipment. And important point here is that biogas technology, usually the components originate from other countries, and also the dimensioning and also the construction details originate usually from countries where a lot of biogas plants have been built, or where the experience of the construction company comes from. And this might not hold true for the country where it is applied. So if you think of Egypt, you're coming from, you are discussing with a technology provider from Europe. Concrete prices, for instance, might be completely different in your country than it is in Europe. So they might recommend a concrete vessel to you, but it might be cheaper in the country to build a steel vessel. So please make sure that you pay attention to such details when it comes to investment costs for the equipment. Operational costs, we have here maintenance and replacement. I've already highlighted or emphasized on the necessary infrastructure in your country. And operational costs are also to be considered in the long term. You don't want to operate your plant only 5 years. You might want to operate this 10 years, 15 years. To make sure that your prognosis includes such a long-term operation. And also the revenues coming from your substrates or from your energy production. You need to consider what is the dependency of your long-term, or what is the long-term development prognosis of your revenues. Do you have long-term contracts for your substrates? Do you have long-term contracts for the energy you are selling? So this is something which you have to consider during the feasibility study. Here I would like to discuss substrate characteristics and in particular the gas potential. Well, first of all, the gas potential. Gas potential is the maximum biogas yield which can be obtained. So this is something like the basis for any process dimensioning or any process evaluation. So you start with a number on what the substrate holds in stock for you. This can be either measured based on a batch test or other test systems. I would like to highlight this or discuss this later on here, or it can be calculated. Second, and also very important, is the degradation rate. That means how fast this potential can be retrieved from your process. So the degradation rate usually defines the retention rate, the retention time to get a certain percentage of your biogas potential. Content of micro trace or macro elements. This is an important number or value to know in order to estimate the stability of your process. Is there a certain deficiency in your substrate and you need to add micro or macro elements in order to stabilize the process or the microbial growth, I should say, not the process. Content of potentially inhibitory substances. There are some substances which can inhibit microbial growth, and then they would inhibit your conversion to biogas. And accordingly, you have to check on these components or substances which are within your substrate and deduce the concentrations which might occur in your process, and then you can estimate if you can expect inhibitory conditions or not. Last but not least, mechanical issues. Is your substrate, once it is in the digester or during your pretreatment process, is it actually pumpable? Can you handle, transport the substrate with your components? And what I have already mentioned several times here, content of disturbing material, sand, stones, pieces of metal, plastics, things like that. Quality of your substrates in general, you can expect that any waste material has usually a variable characteristics, so they change, the composition changes over time and also changes according to the region where you get it from the process where you get it from. And that's why representative sampling prior to your feasibility study or to your construction of your plants or to the selection of your components is crucial. So make sure that you really know what substrates you are dealing with and that you have a robust estimation of the characteristics, gas potential, and also all the other characteristics I have mentioned here. In particular, in waste streams, you have also very often seasonal fluctuations. So it's not only enough that you get different waste streams evaluated, make sure that you also have a good idea how your substrate will change over the course of a year. Here I would like to show you some substrates in regards of their gas potential. First of all, only organic material can produce gas. That's why very often the total solid content and also the volatile solid content are used to estimate the gas potential. So in case you have a literature value or a standard value for a specific substrate, let's say organic waste or manure, and you have a total solid, volatile solid content in your specific case, you can, as a first approach, estimate the gas potential of your substrate. Second, of course, is the biogas potential per ton of substrate. This is in particular important if you have substrates which contain a lot of water. Then, of course, the biogas potential in reference to your tonnage is very low. And this is important if you think of hauling in substrates like manure. So it doesn't make a lot of sense to transport cow manure, for instance, liquid cow manure, over long distances, because you're hauling a lot of water around, and this is not really cost efficient. That's why first to look at the biogas potential in relation to the tonnage of a substrate, wet mass, is a very good idea. Second, of course, is the specific gas potential important, because this tells you how easy degradable, how the gas potential of your target substance in the substrate is. And as you can see, there's a lot of variance in the different substrates, but in general, substrate as energy crops, for instance, corn silage is mentioned here, or rice silage, have a very high specific biogas potential, whereas cow manure, pig manure, chicken manure have a lower specific gas potential, because the substrate or the original organic material has gone already once through a digestion process. So the animal has actually taken out the easiest degradable fraction of your organic material, and in the manure is only what the animal cannot really use or cannot take up. And that's the reason why manures have usually a much lower specific gas potential than fresh organic materials as corn, as rye, or even as separately collected biowaste, because here we have a lot of food which hasn't been used, or which hasn't been spoiled, or now spoiled is the wrong word, which hasn't been eaten before. So it's in food waste or in separately collected biowaste, you usually find residues from meals and also from cleaning up food. And that's why also separately collected biowaste has very high specific gas potential, but also per wet mass, the gas potential is actually quite high. And then there are two examples here at the very bottom: lipids from a grease separator, or glycerine, which is a byproduct from biodiesel production. And these, of course, such industrial wastes can be very valuable co-substrates for your overall processing, because they contain a lot of gas potential. I have mentioned that a good evaluation or precise evaluation of your substrate characteristics is very important for good dimensioning, or for well-founded dimensioning of the process. And this you can accomplish by doing tests if you do not want to rely on literature values. Literature values have, as I already said, quite a variance, and you never know if a literature value really meets the conditions of your specific substrate. And that's why a test, a continuous or batch test here in these cases, usually delivers more precise insights into your substrate characteristics. Continuous tests causes a lot of effort, is usually quite expensive, but it allows a detailed assessment of individual process conditions. So you can set such a test right to the retention time you aim at in your full-scale process. So you will gain quite a precise evaluation of the yield you aim at. You can see if there are inhibitory effects. You can actually also deduce degradation efficiency. You can even look at the microbial community building up in your process. So these are all things you can only do in a semi-continuous laboratory test. It takes a while, usually several months, to really establish and evaluate such a process. And this causes, of course, also costs. Second, more common, faster and cheaper test is the batch test. Here you set up a simple inoculum with your specific substrate. You are done after usually 30 days. And you can quickly evaluate the gas potential based on such a test. There are standardized protocols available, and such a test is much faster than the continuous test. But the results they have a certain standard deviation, so the precision is not very high on a batch test. In particular, if you want to transfer the results to a full-scale application, to a continuous operation. And this is due to the fact that there are many influencing factors like the inoculum, experimental procedure, measuring techniques, things like that. So that's why the batch test is the more common, but actually only the second best choice in testing substrates. As said, the tests deliver different results. It's not only important to know the gas potential or the gas yield. From batch test you would actually gain the gas potential. From a CSTR system you would get, in the first place, a certain yield at the specific retention time you're operating at. And here in these two graphs you can see that both systems are of course dependent on time. I already mentioned the degradation rate, and at a certain retention time you obtain a certain gas yield in dependency of your degradation rate of the substrate. So the K value, which is given here, is actually ruling the fraction of your gas potential you obtain from your process in a certain period of time. Problem is that the K value, which is in a chemical process transferable from a batch to a CSTR system, we haven't found that in a full-scale application during analysis of lab results, that this is not transferable. That's a little bit a problem, that you can do a batch test and you obtain only the gas potential, or you have to calculate the gas potential based on the yield you obtain in the batch test. There are different approaches to obtain gas potential from the results of a batch test. However, at the end you have a gas potential here, and in a CSTR you obtain, as I already said, only a yield if you run a CSTR system at one retention time. If you want to obtain the gas potential, you need to operate several digesters at several retention times, and then you can calculate this curve you can see here based on these points. Again, it's not possible to transfer kinetics from a batch test to a CSTR system. Research comparison has been showing that batch tests tend to slightly underestimate the gas potential compared to a CSTR system. You find this in the reference I have given to you here in this slide. There are some results compared. So it's difficult to give really a comprehensive picture here, but as said, the batch tests tend to rather underestimate full-scale or continuous testing results. Second, I would like to discuss a little bit on substrates characteristics, yield, gas production rate, and organic loading rate. Again, since the substrate characteristics are, or the degradation rate is substrate specific, of course also the dimensioning of the plant and the yield you can obtain after a certain retention time is substrate specific. And a long retention time results, of course, in very large digesters. So if you have a digestion volume of, or if you want to establish or design a process with 30 days retention time, then you need digest a volume of 30 times your daily input. So if you want to have a higher yield, then you would try to double your retention time. Then you get a higher yield, as you can see in the blue curve here in this graph on the right hand side. However, doubling the retention time of from 30 to 60 days means you need twice as large a digester volume, and this translates directly into investment costs. And this is the point where you have to actually make the decision between a very high yield and the other factor, which is given here as a specific gas production rate, which means specific gas production to the volume of the digester. So the shorter your retention time, the higher your organic loading rate, and the higher your gas production in relation to your digester volume. And this would be theoretically the dotted line you can see. And due to the limitation of anaerobic process, you need a certain doubling rate of your microorganism. You cannot turn a digester into a 2-minute retention time unit if you want. So usually a CSTR system, you would think of at least 5 to 6 days of retention time, which would already require a very easy degradable substrate with a high content of already dissolved substrates in order to make life for microorganisms as easy as possible. But above, let's say, 7, 8, 9 days retention time, you can actually operate a CSTR system with easy degradable substrates. And then you can follow the line, the black line you can see here, then your specific gas production rate specific to the volume of the digester will decrease in a similar fashion as your yield, so your specific gas yield in relation to the substrate you put in increases. And these two curves you have to consider when you design your plant, and according to your substrate you have to choose how high your yield and how low or how high your specific gas production rate shall be at the end. This relation you usually put into a so-called first order kinetics. This is a simplification of the microbial processes and the mass transfer. So let's say essentially the technical details of such a process is all summed up in a so-called first order kinetics. So they fit the process of a CSTR system well enough to design the process. However, there are other models which can give more detailed information on the processes within, but for our purposes here, the first order kinetics is functioning as well. You have seen the equations of this first order kinetics on other slides here already. Here again it is given, so if you would like to calculate that, you can easily do this with this equation here. And I have depicted here simply two different curves. One is a k value of 0.2 and the other one is a k value of 0.1, just to show you the difference between these two potential substrates, for instance. And you can see after 29 days retention time, you obtain, in case of k value of 0.1, approximately 74%. In the case of k value of 0.2, 85% of your substrate gas potential. The more you move on with the retention time, the higher your retention time is, the higher your yield is. You can see at 71-day retention time, you get 88% out of your substrate 1 or 93.4% out of your substrate 2. So again, this is what you have to consider when you decide for a certain retention time of your substrate. Make sure you know how fast your substrate is degradable and how much gas you want to get out of the substrate. Sometimes also other factors play a role. If you have, for instance, a post-treatment process, an aerobic post-treatment process, you might need some organic material left in the digestate in order to have an active post-treatment after the digestion process. And then of course you will not aim at a complete degradation process during your anaerobic digestion, because the more you convert into biogas, the less activity you will have in your post-treatment. So all those things have to be considered when you design your process. Mass balance of a biogas project is, as always, mass balance. You have a certain input, you have a certain output. Input material is your substrates. You might add additives or water. There might also be a certain recirculation process of liquids, for instance, but depending on where you put your mass balance border, it might not really impact your mass balance. And the output out of the process is usually biogas and the digestate. A CSTR process is usually simplified to the assumption that the changes in the process are zero. So under so-called stationary conditions, you assume that your input mass flow is constant, your conversion rate is constant, and your output is constant, which is not true. It's simply impossible to have this all perfectly constant, but this simplification is good enough to make appropriate estimations to design the process. So what is not really easy is to go into the details or go into the fractions of your substrate. So it doesn't make sense for a biogas process to balance the overall masses, so simply ton per day in, because for the gas production, the decisive fraction is the organic fraction, which comes with the substrate. And if you have only 10% total solids or 15% total solids in your substrates, then it is more appropriate to look into this fraction and not in the overall masses. And this is what is stated here, that usually mass balances relate to the relevant fractions within the substrate. And this can be done based on the total solids. More often on waste or agricultural products, it is done on volatile solids. Within the wastewater sector, usually chemical oxygen demand is more the basis. Science and also modern wastewater treatment facilities go after the total organic carbon, TOC. Feed value analysis has been applied when agricultural substrates are used. And elementary analysis is some scientific evaluations which has been done in the past, but this doesn't help a lot when it really comes to practical plant calculation. Here you can see a mass balance, an example of a mass balance. This is a maize silage, so this is an example from Germany, and here we use energy crops, and one of the major energy crops is maize silage, but this is simply an example. It doesn't matter if here is silage or waste material. You can see on the left hand side the input characteristics, and then you can see how much of how many tons per day get into the plant, what's the total solid content, what's the volatile solid content, and then what fraction of this volatile solids is actually degradable. And second, you can see the mixture, the mash, because there's also some process water added here, and then this goes into the digester, and there's a certain retention time given, a certain degradation rate, and a certain digester volume. And here a certain efficiency is actually calculated based on these values for this process. And then the mass of digestate comes out here. We have a certain mass of biogas going out, and the digestate is essentially the mass of substrate minus the biogas. And then we have total solids, volatile solids, all the fractions which are left in the digestate. And we have, of course, a certain residual gas potential in the digestate, because the process with a given retention time cannot convert 100% of the gas potential. Mass balance, why should you do that? Because first of all, the mass becomes visible. You really can calculate what your digestate masses are, what content of total solids you have remaining in the digestate. You can actually check on the performance. So if a contractor tries to sell you 20% more gas out of your substrate with a certain retention time, you can check on plausibility with a mass balance. You can check on potential for optimization. So if you decide for a pretreatment, substrate pretreatment unit, you can also check for plausibility if actually your masses allow such a pretreatment and what the potential for yield increase is actually. If you have a post-treatment, you can calculate what mass is to be treated there. Important, based on the biogas residual, on the residual gas masses, you can of course estimate emission potential from the digestate. Do you have to cover the digestate storage or not? You see the concentrations of substrate within your digester medium, and you can also upgrade your mass balance if you're interested in other fractions, for instance, nitrogen balance. So if you need to estimate what your nitrogen concentration, in particular ammonia concentration in your digester medium is, you might need that for estimation of inhibition, then you can easily upgrade such a mass balance by nitrogen. This only holds true for a stationary process. As soon as it gets to instationary processes with a lot of variation in substrates or an input feeding rate, then you need a more dynamic model, and this is much more sophisticated than such a first order stationary model as you can see it here. Here I would like to discuss some options for the gas utilization. I have discussed now gas potential, gas yield, mass balance. Now I would like to highlight some options for gas utilization. In particular, in regards of the process steps you require then downstream from your digestion process. So when you decide for electricity provision, then you need a certain minor gas treatment. So make sure that H2S, you have a gas treatment for H2S removal, a gas drying process maybe also some gas transportation. But then you already can feed into the CHP unit. Then you need a transformer and a connection to the grid. Or you have a standalone solution, then you need actually somebody who is using your electricity. And very important point to me is the use of excess heat. The heat has to be utilized in a storage or a heat sink, a direct heat sink. And heat is also very valuable energy. In hot areas of the world, you might also use this heat for cooling purposes. But anyhow, I think CHP units should be actually also considered to be as a heat production, not only for the electricity production. If you decide for biomethane to the grid, then you need a little bit more sophisticated gas pretreatment. Then you need an upgrading unit, and last but not least, the feed-in station when you go into the grid, or the filling station for transferring it to vehicles or to gas bottles. This would be the case in the next option, which is named your biomethane to fuel station. As already said, you need upgrading pressurization, storage, and the filling station. You might also use biogas directly to produce heat or to also cool based with the gas. And then you need a certain boiler and facility to convert heat into a cooling system. Any of these technologies result in completely different investment costs, and since they all aim at completely different markets, this results also in different revenues. So decision upon which gas utilization you aim at is made usually based on the potential of the revenues in relation to the investment costs you have on these technologies. Gas utilization units, here you find some technical characteristics of different CHP units. This can be a simple CHP engine, it's a motor, a combustion motor. It could be a gas turbine, micro turbine, Stirling engine, fuel cell. I don't want to read all these numbers here to you. Standard application is the combustion unit, the engine. You can see here on the right hand column, on the most right column. And all the other ones have not such a application, they don't have the same application numbers as the simple engine. Besides the gas utilization, another important point is what to do with the digestate. Usually you have in the digestate remaining organic material, which is actually quite usable, quite important to bring this back on agricultural arable land. This is the first thing. Second is also you have a certain water content. Also the water should be applied back on agricultural land. And last but not least, we have a lot of nutrients in it. These are salts, but it's also ammonia, phosphorus, which is a valuable fertilizer to agricultural practice. And that's why the preferred solution for digestate should be application on agricultural land. And this is also the cheapest solution. But question is there available equipment for application on arable land? What are the costs for transportation and application? And how is your storage capacity on your biogas plant? Because usually the application on arable land is not possible during all the year, so you have to make sure that you have storage capacity. And what I already had mentioned, how's the contract situation? How can you be sure that the digestate can be actually applied most of the time? And in the long term, not most of the time, in the long term, I think this is very important, because once you have problems to get rid of your digestate, you will run into issues on your biogas plant, because the digestate will actually hinder further processing of fresh substrates once your storage capacities are filled. Digestate handling, an option here is also solid-liquid separation. So here you can actually separate out solids in order to condition your digestate for further application on agricultural land, for instance, or in order to condition solid fraction for post-composting process. So this unit you can see here is a very simple solid liquid separator for manures, for instance. You can actually remove fibers and particles, but the more sophisticated your separation shall be, the larger such units will look like, the more expensive they will be. As said, this is a very simple unit here. However, whenever you go for such a post-treatment prior to your final treatment steps, make sure you have checked on what do you actually plan to do with separated fractions, what to do with the liquid fraction, what to do with the solid fractions. Is there equipment for the treatment available? Who owns it? Who has to maintain it? Who has operated it? What are the costs related to this? What is the cost for transportation and application? What is the storage capacity of your plant for times when application is not possible? And again, check on the long-term contract situation. Digestate handling, one aspect is the composting process of the solid fraction. This is an additional step which requires area, because usually you use windrow composting and there's a certain area demand for windrow composting, and you require machinery to actually conduct such a post-composting process. However, compost has the advantage compared to the liquid substrates I mentioned on the previous slides more often, that it is easy to be transported and it's a relatively stable product. So it's not that it is still degrading, it doesn't produce a lot of gas and things like that. So it's a biological stable product. Composting process reduces masses because it's further degradation step, and it also reduces water content, so it's also less costly to transport compost compared to liquid digestates. And composting has also the advantage that it usually results in higher temperatures within the composting process. And this means you have also a sanitation or hygienization, which is also an advantage of a composting process. Now I would like to come to the last major topic here during this presentation, and this is the economy of such a process. First of all, I would like to highlight that a cost-benefit calculation shall be done on a defined period of time. Because if you look in a long term, then the relevance of the investment costs tend to become less important than in a short-term evaluation. The long-term operational costs of such a facility become more and more important, and they are much higher, or they tend to be, could become much higher than the investment costs. That's why maintenance and also working costs or operational costs which relate to substrate and digestate should be considered in any cost-benefit calculation. Also important, replacement and labor costs during operation of a biogas plant should be considered and put into relation to the investment costs. I would also recommend references from the provider of the technology for long-term operation. And in particular, when you treat waste materials, then the gate fee can play an important role in your cost-benefit calculation. The risk coming from variable costs on the waste sector, but also on the security of your digestate utilization should be considered during the cost benefit calculation. In these two graphs here, you can actually see the impact of economy of scale on the biogas facilities. So don't take these numbers as 100% true here. So the absolute estimations on investment costs of agricultural plants will look like different if you would evaluate this today. However, what you can see is actually that the larger the facility is, the lower the specific investment costs get. And this is a very important point, that biogas plants are really highly influenced by economy of scale. On the right-hand side here, you can see that this is not only for the overall biogas plants true, it also holds true for the CHP units. And this is something you have to consider when designing a biogas plant. However, the conclusion somebody would draw from that, as big as possible, as cheap as possible, is contradicted by the fact that you need substrates for a biogas plant, and these substrates are usually not available in indefinite numbers at a certain site you would like to build a biogas plant. They are usually limited. So the amount of substrate available at a certain place usually rules the size of the plant. You can, of course, transfer it, you can buy substrates, but this has natural restrictions due to distances, due to logistics. So that's why the size of biogas plants is usually limited by the substrate availability. However, if possible, you should aim for as large as possible, because then your specific costs decrease. And as already mentioned, with the different substrates, also different costs come with the biogas plants according to pretreatment, according to requirements from authorities, according to costs, to simple costs of these substrates. This results in a completely different operation and also investment costs. If you compare liquid manure, which you can, if you build the biogas plant right on site of a dairy facility, for instance, you can feed your process directly with a simple pump. If you have, compared to that, waste materials, you have to pre-treat that. You have to separate out. You have to separate out disturbing materials. You have to remove plastic, stones, things like that. And that's of course more costly. And also waste materials usually have more requirements in regards of safety, in regards of labor safety, in regards of odor protection. All these things add, of course, costs and result in higher investment costs. And that's why even with comparable, similar plant capacities, investment costs, substrate costs can differ a lot and lead to complete different economic schemes of biogas facilities. On this slide, I would like to show simply the cost distribution of different plant schemes here. So you shouldn't pay a lot of attention to these different systems here, flexibilization options. This is a topic which is very German, so we aim at electricity production when electricity is needed according to the grid, and that's why capacity is added to the biogas plant. If you have a standard application with average capacity output of 500 kilowatt, you can add another unit to have 1,000 and then run this only 12 hours a day. So this is the idea behind this 4 different scenarios here. Whatever, I would like to highlight the cost distribution between CHP, pump station, solid feeding unit, digester, digestate storage, gas storage, just to give you an impression how the cost share between these different fractions is. So, and as you can see, if you double the CHP units, this would be the reference case here, baseload operation and flexibilization upsizing, then you can see that the price of the CHP unit doubles, and accordingly all the other costs are influenced by doing so. And here you also can see that the operational costs on feedstock and resources, in this case here, we could talk about my silage, this comes with a certain cost factor. It has a large impact on the operational costs if you use such substrates where you have to pay for. So when looking at the revenues, obviously if you want to invest in a biogas facility, it's a long-term investment, and that's why that biogas applications usually require long-term stable cost and price situation. This is a very important point, and usually we face in the countries that different tariffs or support mechanisms for various energy forms are available. So you might have a renewable gas tariff and a renewable electricity tariff and even a renewable heat tariff, and then you have to calculate what the best is for the biogas application. Make sure that you also use your excess heat. This is a very important point. And in particular, when you apply waste material, check on the gate fee, what you can obtain from there, but also look into the quality of the waste. Garbage in, garbage out is English saying, which means if you have low quality waste materials, you cannot produce a high quality compost from this. So this is also an important point to consider. And of course, technical issues with low quality waste is also to be considered. Compost marketing tends to be difficult depending on the practice in the country, the knowledge of potential applicants, if you think of farmers or also communities to use the compost within their land, what they have to maintain. So really start early on looking for markets where you can apply your end product. Anyhow, it's much easier to sell high quality compost than to sell low quality compost. And usually the compost tends to be an uncertain variable in the calculation. So I would also recommend also to calculate your business case with the option that there's no income, or you even have to consider discharge and transportation costs of your compost material. So thank you very much for listening to this section here of the workshop. That was about project development, and I hope you enjoyed it a little bit. And as said, in case of questions, don't hesitate to contact me.